Ever wondered how machine learning models know they're wrong and how we measure that? Today, we're breaking down loss functions and metrics, the compass that guides every AI model toward better predictions. At its core, a loss function quantifies the gap between what a model predicts and what actually happened. This error signal flows backward through the network, driving gradient descent to adjust weights and minimize future mistakes. Without it, models would have no direction. Most loss functions follow a simple pattern. Calculate the error for each sample, then average across your dataset. The specific formula you choose, whether for regression or classification, shapes how your model learns. Take mean squared error, or MSE. It squares the difference between prediction and truth. This amplifies large errors, making MSE powerful for regression, but also sensitive to outliers. One extreme value can skew the entire training signal. That's where mean absolute error, or MAE, offers an alternative. By taking absolute values instead of squares, MAE treats all errors equally. Use MAE when outliers are noise. Stick with MSE when large errors truly matter. For classification, cross-entropy is the gold standard. It penalizes confident wrong predictions heavily, pushing the model to assign high probability to the correct class. Whether binary or multi-class, it's the engine behind most neural network classifiers. But be careful with accuracy alone. In imbalanced datasets, say, 95% negative case is a model that always predicts negative hits 95% accuracy yet learns nothing. Accuracy can mask critical failures. That's why accuracy isn't enough. We turn to the confusion matrix dot. It splits every prediction into 4 clear buckets. True positives and true negatives show where your model succeeds, while false positives and false negatives expose exactly where it's failing. Instead of one misleading number, you get a full diagnostic map of your model's real behavior. From those 4 buckets, we extract precision, and recall.precision measures quality. Of all flagged positives, how many were actually correct? Recall measures coverage. Of all real positives out there, how many did your model actually catch? Here's the catch. They naturally pull against each other. Chasing more true cases usually triggers more false alarms, making their balance a fundamental trade-off you must optimize for your use case. The F1 score balances precision and recall using a harmonic mean dot. Unlike a standard average, it heavily penalizes extreme imbalance, so a model can't mask poor performance in one metric dot. That's why, on skewed datasets, F1 gives you a single, honest score that only rewards models performing well on both fronts. Beyond these, specialized losses exist. Huber for robust regression, focal loss for imbalance detection, KL-Divergence for distribution matching. Each encodes different assumptions about your problem. So choose your loss and metric based on your real-world objective, not just convention. Thanks for watching. If this helped, follow, and subscribe.